Adam Rees's childhood love of science led him to major in physics at the Massachusetts Institute of Technology. Curiosity saw him enroll at Harvard Grad School in 1992 in astrophysics.
How old is the universe and what's going to happen to the universe? The fact that science can really address those questions, that you can actually sit down and come up with an experiment to measure those things, was really exciting and interesting to me.
Adam's Harvard advisor was Robert Kirshner, whose former student was Brian Schmidt.
They were having good success with one class of these supernovae. I asked him if he had any good ideas for a project, and he said, what about this other class of supernovae, these type 1A supernovae? They might yield even better measurements than the ones that Brian was working on.
Graduating from Harvard, Adam became a fellow at UC Berkeley in 1997 and joined the High-Z supernova team, which has been collecting supernova data.
I was fortunate enough to be in the position of inheriting that data set to actually analyze, to convert from images, if you will, raw images, to measures of the expansion rate.
The images were coming from telescopes around the Earth and the Hubble in space.
We find a distant supernova that's out there somewhere, and we want to observe it. We want Hubble to point at it all the time.
The Space Telescope Science Institute in Baltimore, which Adam later joined. It's a command post for the Hubble Space Telescope.
When we find a supernova, we have to quickly tell the Institute where to point the Hubble Space Telescope over a series of times so I can measure the supernova on the rise when it reaches its greatest point of brightness. And that tells us how far away the supernova is by how bright we see it appears, and we have to get on it very quickly before it fades away. Every one of these observations is giving me one more measurement in that series of models of the universe.
Chinese researcher Chun Su worked in Adam's team.
He is very diligent, very careful. Yeah, he always pushes to the limit to get the best results from the data.
And some unusual results were precipitating from the data.
Very exciting, really exciting, because it's like we really see something that's totally unexpected.
It was 1997. They still believed the universe was decelerating, but measuring the brightness of supernovas, they found otherwise.
If the universe was filled with matter and that was slowing down the expansion rate, the supernovae would fall along a line like this that says constant deceleration. These are the nearby supernovae that tells how fast the universe is expanding today. These are the distant ones, and they are showing us that that expansion rate is speeding up because they were very faint, which implied that they had gotten very far away in a short period of time.
And these distant supernovas being charted fall on a line in the upper quadrant.
This direction up here would imply like negative mass, which doesn't make any sense. Because there can't be negative matter, the only alternative is this thing that Einstein had called the cosmological constant, a material with a negative pressure that has negative gravity according to general relativity. And that would act a little bit like negative mass.
The broad term dark energy was coined later.
It's one of the most significant discoveries in recent years, and probably even in the past century. This dark energy that they discovered is 74% of all the energy of the universe. It's not some small part that we can absolutely ignore. It's like, imagine, if you look at the Earth's surface, it's covered 70% in water.
The big question now in cosmology is, what is the equation of state of the dark energy? And that will tell us whether it's a very strong dark energy, like the one on the right. That would be like Einstein's cosmological constant. If he was right in the beginning, it's that piece of physics, then it's very clear that the universe expands forever.
Which means in billions of years, if one looks at the sky, there will be nothing there.
I really thought that discoveries are things only made by people in old grainy black and white pictures in textbooks. I didn't in one of my wildest dreams think that, we'd make a discovery of something. Okay, Gabby, should we get out now?
The discovery coincided with another milestone in Adam's life, his marriage to Nancy in January 1998.
On the eve of our honeymoon, and I was exchanging all these messages with my team saying, oh, I think we discovered this, I'm not sure, we should check this, we should do this. And of course, it was bad form at the time, was you're about to leave on your honeymoon to still be working. But
the bride is waiting. Can we go? Can we go?
I was trying to describe to her, I said, you know, this is a really big discovery. This is a really big deal. But of course, you know, we don't, I mean, you know, it's the only thing I've ever worked on. So, you know, you don't really know if it's going to be a big, big discovery.
Adam and Nancy had met at MIT.
I was studying physics.
And I was studying engineering, material science and engineering.
Can you say star?
Duh.
Can you say daddy?
Daddy.
Can you say mommy?
Mommy.
Daughter Gabrielle is 2 years old.
She can say star. We're working on supernova. I know that as she grows up and learns more about what her father has done and the awards that he's won, she'll be so proud of him. So that's amazing.
I look forward to explaining it to her. So.
Yeah, I reanalyzed some of the data from the past cycles just to compare.
Sometimes one gets the hot pixel and the other doesn't, sometimes vice versa. So
Today, Adam and his colleagues at the Space Telescope Science Institute continue using Hubble to get even more detailed information from supernovas. But the Hubble's fate is linked to that of NASA's space shuttles. Now the telescope's future hangs in the balance.
if the space shuttle cannot fly, then the Hubble will break down at some point. Now, the astronauts are scheduled to return in 2007 for the last time and put a new camera in, which will help us do this research even better. The space shuttle will be retired in 2010, and so there won't be a space shuttle anymore. Maybe the next vehicle, which is called the Crew Exploration Vehicle, maybe it will be able to reach Hubble, maybe not.
But until that day comes, astronomers will continue to use Hubble to try to unravel the secrets of the universe.
Over in Australia is another Shaw laureate for astronomy, Brian Schmidt.
I always wanted to work on big problems I can explain to my grandmother. And that was a problem I could explain to my grandmother. Was the universe going to live forever, or was it going to, collapse on itself? Saul Perlmutter and his group, before even I started graduate school in 1988, were using Type 1a supernovae to try to measure cosmology. Those of us studying supernovae had our doubts about the actual ability of Type 1a supernovae to be used as useful distance indicators. I decided, well, it's great for Saul to be doing it his way, but I thought that we, the supernova community, should do our own attempt to use supernovae to measure distances.
That led to the formation of the High Z supernova team in 1994. 22 members working at telescopes in Chile, Hawaii, Europe, the US and Australia.
I was sort of the jack of all trades, and I wrote the software to find the object.
The software was supposed to clean up snapshots of the sky of thousands of galaxies, enabling them to identify supernovas.
I elected to stay in Australia and coach the Chilenos in finding supernovae with this untested software. That was nearly a disaster.
When his colleagues in Chile tried using the software, it didn't work.
I would try to guess what the program was doing wrong, and I'd send them a little code update. They'd run it, and they'd tell me over the phone, well, this is what it's doing wrong. And I ended up writing these little stamps. It would send me these little, tiny little 16 pixel by 16 pixels of things. It was saying, I think this is a supernova, and they would inevitably be junk.
Just as the team was about to throw in the towel, one image looked promising.
This is supernova 1995K, and it's the little blob on the side of this bigger blob. And we discovered that in the end of March 1995, which sort of got us going.
What would you have done without it?
I think we would have folded up and died.
1995K proved the software worked, and the High Z supernova team was on the right track.
We would go through and use those spectra to measure the distance, and then we'd accumulate all this data, and then over the next year we would process it very, very carefully to measure exactly how bright the supernova was on each day, so that then we could put it through our distance fitting methods.
One method was measuring something known as high red shift. When a supernova explodes from nearby, the light appears blue. As the light travels towards us and the universe stretches, its wavelength stretches. By the time it reaches us, it appears red.
Type 1a supernovae sometimes had dust between us and the supernova, and that dust made the supernovae appear fainter. The dust also makes the light of the supernova a bit redder. And so we, from the very beginning, worked out a system by which we would observe the objects in two colors and take account of this dust.
Tensions were starting to run high between the High-Z supernova team and Perlmutter's supernova cosmology project.
I, fortunately, being here in Australia, was somewhat removed from what was going on in the US, but I would get periodic reports of various disagreements that happened at conferences. These big things. We were trying to figure out what the ultimate fate of the universe was, and you didn't want to be second in that race. You wanted to be first. By 1996, we had our first measurement. By 1997, we had 4 measurements, and they were all showing that the universe was not slowing down much. This was in contrast to a result that Perlmutter and company had, which was saying the opposite, that it was slowing down a lot. Little did we know that they were actually getting the same crazy answer as we were.
That the cosmic expansion is accelerating. Brian Schmidt was born in Montana and raised in Alaska in the United States of America. After completing his PhD and his postdoctorate at Harvard University, he came here in 1994 to Canberra in Australia.
Ken has many, many years to hone his, and mine still.
Brian splits his time between teaching at Australian National University and Mount Stromlo Observatory, just outside of Canberra.
So this is the 50-inch Great Melbourne Telescope, which I used to look for supernovae in the relatively nearby universe, and this was complementary to the work we did in the very distant universe.
The telescope where Brian did much of his early work was gutted in a bushfire in 2003.
This feels sick to your stomach because it's, you know, it's almost like losing a member of the family. It really, it was devastating.
Once you've got the code, once we get the 6 filter slides, and you'll have the code effectively ready to do the final test.
But out of the ashes rose a new project, SkyMapper, a telescope with a high-resolution digital camera, due to be completed at year's end.
All right, it's looking good. It's going to be able to look at a piece of sky about 40 times the size of the full moon simultaneously, and that's down to a resolution which is as good as you can literally do. It's an enormous amount of information. We're trying to map out the galaxy and find very rare stars that were the first stars formed in our galaxy when the universe was probably only a few 100 million years old. And by looking at those stars, we're hoping to understand how galaxies and the first stars formed. When I was 8, I became interested in astronomy, and my parents bought me a subscription to Astronomy magazine and a telescope, a little telescope. And so I would play around with it. But I was always convinced I was going to be a meteorologist. My passion has always been not for astronomy, but for science. My father is a scientist, a biologist, and so I got to see the scientific process, the idea of figuring things out.
Brian's other passion is his vineyard of Pinot Noir grapes.
There's a lot of science behind making good wine. And in astronomy, there's a little bit of creativity and a lot of science. This is my artistic expression of life, and it's just something for me to relax and to think about something other than astronomy. This barrel is just a little smelly, and I can correct that with a little bit of copper. Turns out copper binds up with sulfur.
Brian's two worlds feature on his wine's label, a starry sky above a vineyard.
Hi, Dad.
How you doing?
Rare family time at the Schmidts. Brian and his wife Jenny, an economist, travel a lot.
The vineyard's meant to keep him here.
The two met at Harvard and married. When Jenny returned to her native Australia, Brian came too.
That's a long way away from where a lot of recognition is, so it's really nice that even though he's here, he can still get some really good recognition.
That recognition came after the team published 3 papers laying out proof to the scientific world that the expansion of the universe was speeding up.
I was very insistent that the young people would write the the papers. And so I said, I'll write the first one. And then we drew straws, and Peter Barnovich got to write the second paper. And then Adam Rees, who was just finishing his PhD, got to write paper 3.
Adam's paper, published in May 1998, set the scientific world abuzz.
Adam Rees's thing that he does better than anyone else on planet Earth is knowing how to measure distances accurately.
When everybody looks at the night sky, it naturally makes you wonder questions like, is the universe infinite? Will the universe last forever?
And Professor Saul Perlmutter has led the world in finding some answers. As a graduate student in physics at the University of California in Berkeley in the 1980s, Saul began looking for exploding stars, or supernovas.
They're caused when one star is dumping a little bit of matter onto an old burned out star until there's just enough material on that star that it reaches a critical mass and explodes in this vast explosion. The brightness of the supernova tells you exactly how far away it is from us. If you know how far away it is, you know how far back in time the explosion occurred, because you know that ever since that time the light's been traveling to us, and we know how fast light travels.
This made supernovas great tools for measuring vast cosmological distances and specifically how much the universe has expanded. After getting his PhD, Saul joined the Lawrence Berkeley National Lab and helped start the International Supernova Cosmology Project, a group he soon headed.
We have it just when the supernova just exploded. You probably can't see that, it's so dim.
But it wasn't easy to find supernovas.
They explode only a couple of times per millennium, so they're really rare. They give you no advance warning, just random explosion, and they rise and they fall just within a few weeks or months.
So here is the galaxy, and next to it is the supernova, right?
The group eventually developed cameras for telescopes that are able to observe large areas of sky and tens of thousands of galaxies on any night.
The concept then became difficult because now you have to find the little spot of light that's the new supernova in all these little faint blue specks. Each of those is a distant galaxy. So we had to develop a lot of computer software to do the image analysis. We did eventually get to the point that we could have the computer home in on just one of the galaxies and find the galaxy that 3 weeks before has no light and 3 weeks later shows you a brightening.
The aim is to chart the supernovas at their maximum brightness to measure what's happening with the universe.
So here's a light curve, so we can catch it right at maximum.
Saul worked with about 8 people.
We were just running around between offices, basically trying to get all the details checked. It was really a very exciting time.
When Saul tried to convince people that he could find lots of distant supernovae so that they would give him time on their telescopes, people didn't believe him, and that made it very hard to go ahead.
Once we could guarantee a batch of supernova discoveries all at one time, we could schedule telescopes all around the world to follow the supernova as it brightened and fade away.
Saul's group worked with many other astronomers on the largest telescopes on Earth, as well as the Hubble in space. Thus, a project which began in 1988
took us till 1997 for us to actually have 42 supernovae, a batch of supernovae from all different times back in history that could tell us about the expansion history of the universe.
Around 1930, US scientist Edwin Hubble had showed the universe was expanding. The question then was, how fast has it inflated, and is it slowing down? There were 2 schools of thought. One, that the distance between galaxies was growing, but was slowing down because of gravity. The second option was the galaxies would be moving apart, but after a while, the gravity would be so strong the universe would stop expanding and eventually end in a big crunch. But the data Saul and others were collecting showed the universe was expanding at an accelerating rate.
That means that eventually everything will move so far apart from each other that it will take forever for light to reach you from a distant star or galaxy. And that means that when you look out, if you still have a human being to look out, you wouldn't see any stars or galaxies far away. So this was a shock that something as basic as the fact that the universe is speeding up can't be explained easily by the current elements of our physics story.
The discovery was unveiled to the world in 1998.
Saul was the one who had the determination to push ahead with this.
He's a very smart guy.
He's a good team player, good team leader.
Yeah, pretty good.
Very effective, very focused.
It took a while for it to sink in that this actually was going to change the paradigm of cosmology.
The discovery evoked a whole new mystery.
All of the most respected theorists, we have no idea what is causing the acceleration of the universe. It could be a new energy spread throughout all of space, and we call it dark energy just to mean that we know nothing about it practically. Possibilities are endless. Perhaps Einstein's theory of relativity that explains gravity isn't quite complete. To try to understand what exactly is causing the acceleration, we need a much, much more detailed, precise measurement.
And to look for ever older supernovas. To that end, the Berkeley lab is helping develop new sensors.
That when you look at very, very distant supernova, their light is now red. And so you need a way of measuring this very, very red light with extreme sensitivity.
The sensors would be incorporated into the Supernova Acceleration Probe, or SNAP, a 2-meter space telescope that may be launched by 2013 on a faraway orbit to a stable location called the Lagrangian, or L2.
And look out much, much further into the distant cosmos using a camera that's very, very wide. So you can see many, many more galaxies all at the same time.
Here's a model of that camera.
Current Hubble Space Telescope has a camera that's equivalent to just a little piece of one of these squares down here. And this one is hundreds of times more area that you see on the sky with every time you take a picture.
While not looking at the stars, Saul Perlmutter, who studied physics at Harvard, also teaches the subject at Berkeley.
I began with this course on and the physics of music as a way of teaching non-scientists the approach that scientists use. And then tap it, the other one doesn't respond. I was interested in trying to use music as a way to focus their thoughts on something that they enjoy, but little by little teach them ways of asking questions about the world.
Music is also a mainstay in the Perlmutter household, a favorite of 3-year-old daughter Noah.
You give me one-man band?
Yeah.
Saul met his wife, Laura, through her advisor for her PhD thesis on Korean anthropology.
I was very happy to meet Saul. I'm very proud of him. I don't wonder that much about the universe. I figure it's expanding, and whatever happens billions and billions of years from now is not going to affect my life one way or another.
The really big questions in my mind are how does the world work, and also how does the mind work? And a lot of what anthropologists are trying to figure out is how people think. And so in that sense, it's an area that I've always been fascinated by.
Saul has played the violin since he was 7 years old.
I liked the idea that if there's an interesting problem, you learn what you need to try and solve it. And it's a very free, playful approach to the world and to science.
An approach for which Saul has won world acclaim.
Nowadays, so much of science is such a community effort. At least the Shoah Award is something that's being shared between at least 3 scientists as representative of the whole larger groups.
Human skin, once damaged, is replaced automatically. A tadpole becomes a frog after losing its tail. These natural phenomena are all related to the way our cells are programmed to die.
Apoptosis is an essential process for normal life. This process could also somehow go wrong, and that will result in disease.
One man spent decades studying this process.
Cell death will somehow become defective. The cell will accumulate and become the cancer.
He discovered the mechanism of cell death, and with that knowledge, he hopes to find the ultimate cure for cancer.
Even lots of frustration, but every day is a new beginning and full of anticipations.
Dallas, Texas. 2 decades ago, few Chinese lived here. Wang Xiaodong was one of them. Wang Xiaodong graduated from Beijing Normal University in 1984, just a few years after China reopened its bamboo curtain and let its young people study abroad again. Xiaodong seized the opportunity and came to Dallas on scholarship in 1985.
The floor I work on when I was a postdoc. I come back all the time, and I really like this place.
It's here at University of Texas Southwestern Medical Center that Xiaodong began exploring his first major research topic, cholesterol.
I got a chance to work with Dr. Joe Goldstein and Michael Brown. And these two scientists, I have to say, are a very few greatest biologists in 20th century. And they won the Nobel Prize when they were 44 and 45.
During his research, Xiaodong identified a protein which he at first thought was only responsible for controlling cholesterol level. But further scrutiny revealed otherwise, that the protein plays a much more important role, triggering cell death. The discovery changed the direction of his research. He began studying, with more zeal than ever, how this protein initiates apoptosis, the self-destructive biochemical process in our cells. Xiaodong did research day and night, taking breaks only to have dinner with his family and returning to the lab till 1 or 2 in the morning.
You don't notice the time passed. You can look into the microscope for hours because you are looking for something. And, it's like a treasure hunt.
Every day he did the same experiments, only to get disappointing results. But he wasn't deterred.
When I first started, as a graduate student, I took the failure very hard. I often was so upset that I just simply couldn't go home. I have to drive around the school until my emotion quiet down, then I can go home. But tomorrow morning is another day. And I cannot wait to come to school, to the laboratory, because now I have more ideas. The more ideas that I can improve upon on yesterday's experiment.
In 1995, Xiaodong founded his own laboratory to further his research in apoptosis. After more than a decade of painstaking research, he reached a breakthrough. It not only won him academic recognition, but also shed new light on cancer treatment and medicine. The human body is made up of more than 10 trillion cells. An automatic mechanism regulates the birth and death of cells. Each day, billions of cells die and are replaced by fresh cells. Human well-being depends on the proper functioning of apoptosis, which keeps cell death and cell birth in perfect balance.
And this process could also somehow go wrong, and that will result in disease. And there are 2 types of diseases that can be resulted from defect in apoptosis. One type is the apoptosis can be sort of accidentally or undesirably turned on.
Which means more cells die than are born, causing organs to degenerate, as in Alzheimer's disease.
The flip side is cancer. You have growth, but without death, and the cell will accumulate and thus contribute to tumor genesis and become part of the cancer.
Xiaodong wanted to know, what is it that keeps apoptosis from functioning properly? Every human cell contains many mitochondria, which oxidize food and generates energy to keep the cell alive. When a cell is programmed to die, the mitochondria release a protein called cytochrome C to set the suicide process in motion. But the cell may release proteins called IAPs that act as a shield against cytochrome C. The mitochondria will then try to overcome this resistance by releasing another protein called SMAC to neutralize the IAP so that apoptosis can resume. After discovering this previously unknown mechanism, Wang Xiaodong successfully created a molecular mimic of SMAC, which can be a powerful weapon against uncontrolled cell growth and thus cancer.
The idea that we have is whether we can, by understanding the precise pathways of apoptosis in almost that's all cell use, and then looking for what the particular roadblocks the cancer cell apply to keep them alive. And then whether we can use small molecule to specifically remove that roadblock. And in theory, and that will not affect normal cells, and that will specifically make cancer cells sensitive now to apoptosis.
Xiaodong lives in Dallas with his family. His wife Sherry has 2 PhDs and is a medical doctor specializing in rheumatism. She met Xiaodong at UT Southwestern. Their sons Alex is 16 years old and Daniel 5. Xiaodong says he feels blessed to be together with his loved ones, a luxury he rarely enjoyed during his childhood in China.
That's my grandfather. After I finished college and he came, he visited me, and 2 of us decided to go to Great Wall.
That was his grandfather's way of seeing him off to America in 1985.
This is my grandma, who basically raised me. We have lots of great memories together. And even now, when I think back, I realize how strong and how smart and how loving she is. I really miss her every day.
Wang Xiaodong's parents separated soon after he was born in 1963 in Henan province, China. He was brought up by his grandparents, who were both teachers. The Cultural Revolution broke out when Xiaodong was 3 years old. His grandparents were harassed, and his great-uncle, a biology professor, was dubbed a counter-revolutionary and sent to the countryside to work as a farmer.
And every summer and winter vacation during my school years, my grandma would send me there to spend some time with him. And he talked to me about biology all the time and what he does, and it really fascinates me. And also, even though he lived in a countryside, and he lived very gracefully, he always nice to everybody and talking to them. And I think that's also influenced me a great deal and shaping me who I am.
But his great-uncle didn't live to see him take up biology in university. He died of liver cancer, just as the Cultural Revolution came to an end. Xiaodong's mother also died of the same disease.
But I do remember, when my mother died of cancer, and my great-uncle, this brother of my grandma, died of cancer. I did feel this, sense of helplessness, sense of despair, that I wish I could do more. I could do something, to help them. But of course, I couldn't do anything. So I guess that sense of helplessness stick with me. Maybe subconsciously, I wish through my work, I can eliminate or alleviate this sense of helplessness.
Xiaodong says he's greatly inspired by his family's courage and steadfastness in face of hardship.
他们那代人，经历了太多的这个生离死别，他能够还是心里非常坚强。I think back, I realize, that generation of Chinese people are really such a wonderful people, and they have so much love between them and so much dignity and grace.
Chinese wushu novels, especially those by Louis Cha, are another source of inspiration for Xiaodong.
I think his novel really have beautifully written, language-wise, and also he has this characters, the heroes, and that make you fancy yourself and make you inspired to be a hero, to do the right thing. Being a scientist, study questions and problems that may make people's life better. I guess in this sense, it is heroic. You want to play basketball with me?
He's even named his younger son Daniel after his favorite character in Louis Charles' novels, Wang Chongyang. Alex's Chinese name, Jianshi, carries special meaning too.
His Chinese name has two characters. The middle character is sword. The last character is stone. So with this name, I wish him to be strong as a stone, and as sharp as a sword. So I believe, being a minority, live in the United States, and you need to be strong and you need to be sharp.
Almost all of the 20-plus researchers at Wang Xiaodong's lab at the Southwestern Medical Center are from mainland China. They are now working on the molecular compound Xiaodong created, which has already been proven effective in activating apoptosis in mice. The next step is to make the compound into an anti-cancer drug to be tested on humans.
Human metabolism may be different than animals. Whether this compound will be toxic to human, and that we have to do many more research to achieve that, to eventually able to put in human and see effects in treating human patients.
Sherry Zhu says Xiaodong has always aimed high, ever since his graduate school days.
He has visions in research, so he doesn't care daily in and outs, gain and losses. He wouldn't put most of his effort and energy in homework, for example, or teacher's assignment. Instead, he would talk to individual scientists, learn their theory, learn their system. So in that way, I think he's a little different from most of the graduate students. In a way, he learned the essence of research at a very early stage. He's very intelligent, passionate, so that's the kind of character I like.
In 2004, Xiaodong, at the age of 41, was elected to the National Academy of Sciences. He's the youngest ever Chinese scientist to become an NAS member. But he has no plans to rest on his laurels. Ahead of him is the vast uncharted waters of biochemistry and his lifelong goal of bringing China to the forefront of the field. The Zhongguancun Life Science Park on the outskirts of Beijing. Its flagship establishment, the National Institute of Biological Sciences Beijing, also known as NIPS, was founded 3 years ago with funding from the Chinese government to nurture talents for this quickly expanding field in China.
这种细胞都是死的时候成团。
Wang Xiaodong was invited to Beijing to help set up NIPS and was chosen among 160 shortlisted candidates to be its Director General.
你们吃了是吧？
Xiaodong flies here from Texas once every 2 months to keep informed and to make decisions, often over lunch.
但这个仪器，大家别人会不会有用？
你这一个小摇床就那么大，要6000多美金，你买它干嘛？国产的一样用，效果一样的好。
所以这种事儿就你们把关了。
是，我们就想
所以仪器委员会就是要做这个事儿嘛。
It's people, not hardware, that's Xiaodong's top concern. NIPS need to recruit top scientists from around the world to become a truly internationally competitive research institute. So far, 19 laboratories have been set up here, all headed by Chinese scientists hired from the US.
We try to recruit the best people, the best scientists back to China, create an environment that they can really do great science. We want to get the best people from wherever they can come, but they end up best people are still in the States right now.
The 12-hour time difference between Beijing and Dallas means Xiaodong has to work almost around the clock.
A lot of things, some administrative stuff you need to take care of, dealing with emails from the US. You need to get informed, and you want to have your input.
On each of his trips to Beijing, Xiaodong goes to NIPS as soon as he gets off the plane and immediately circulates the building to check on his colleagues' progress.
Have something to do. I wouldn't say I like busy, but I wouldn't mind busy.
Xiaodong's directorship is an unpaid position. He says that makes it easier for him to ensure NIPS's independence.
This will be the first institute founded by the government, but administrated by a totally new mechanism, which is by this board of directors. The scientist here does have much more freedom. The administration here has much less restrictions, so they can concentrate and pursue science. But whether this kind of mechanism will survive, depend on lots of help, the understanding of the officials.
Beijing Normal University, Wang Xiaodong's alma mater. Today, many students here aspire to follow Xiaodong's footsteps in basic science. One of them is Zhang Yan. Botany major Zhang Yan has just finished her bachelor's thesis and is planning to study in the US next year. For now, she works at NIPS as a lab assistant. Her job involves non-stop experiments from 8 a.m. until 7 p.m. every day.
At first it was fun doing experiments. After a while it wasn't fun anymore. Some parts are really boring. In school I didn't have to do a lot of experiments. Here I have a heavy workload. It's very exhausting.
Zhang Yan says she's starting to get disoriented, spending day after day on experiments that might lead nowhere.
I feel upset, very unhappy. Sometimes I would think, what should I do now? Why can't I get the right results? Then I would wonder if it's my fault the experiment isn't working.
大家看，这是一个非常美丽的一个女孩。
On the stage, Xiaodong gives a lecture to a group of students. It's about two Nobel laureates' lifelong struggle to discover cholesterol.
这么年轻，然后她的血管堵塞，她的寿命这么短，使这两位医生有了一个很好的一个研究的一个系统，而且他们对这个系统有很强的这个 passion， 因为他们知道，我们唯一能救这个女孩子的办法，就是了解她为什么会这样。
His message to the students: think big, stay focused, persevere. Zhang Yan takes the opportunity to voice her frustration.
我回家的时候，我很多人都说你在做什么？我说我在做研究。他说你做这个研究能干什么？我说我也不知道能干什么，就是这样的感觉自己很 frustrated。
你目前还没有一个更好的选择，你要看看你能不能 take a little pleasure。这个既然走到一起，就说明有缘分嘛，是吧？
Zhang Yan isn't the only one in the audience feeling discouraged on the long, hard road of basic science research.
那在研究遇到低谷，就是很大的低谷的时候，那你觉得应该怎么办？或者，你们以前的经历？
我们的经历就是遇到低谷不能停，就是往前走吧，反正看不见也往前走，然后总是会慢慢的走出来。
Xiaodong's advice to Zhang Yan:
我觉得要学会自我调整。对，因为这个我们总可以 blame environment is not good enough. It's never going to be good enough.
These young aspiring scientists may have their doubts, but Xiaodong is impressed by their enthusiasm.
I think the most impressive part is they are very hungry, and they are hungry for knowledge. They are hungry for success. I never seen anything like that before, and only in China.
On this trip to Beijing, Xiaodong brought along his son Alex and his goddaughter Tingting.
Oh, this is just positive control. There's also PCR product.
Alex and Tingting have just started studying biology in high school in the US and are here to get a taste of real laboratory work.
I can spend some quality time with them and in doing something that I've been doing, and also introduce them to scientific research and to see whether they will, what's really working in the lab really like.
They're given an assignment like the graduate students working at NIPS.
I want them to make a specific mutation on a protein that we know involves in apoptosis, and we suspect, it's an enzyme. We suspect, its enzymatic activity might have something to do with cell death, but we don't know.
This is the first time Alex has ever observed human cells under a microscope.
Did you have fun?
I think that it's a good experience to see what lab work is really like. It's not all just pipetting stuff and then putting it in machines. You actually have to think of experiments and implement them.
On this day, Xiaodong takes a rare half-day break off work to take Alex and Tingting on a tour of the nation's capital. They are thrilled to be on the Great Wall.
Wow, look at that. Go.
Alex and Tingting sprint all the way to the tower on the hilltop. Xiaodong is never far behind them. Coming here again after 2 decades brings back many memories for Xiaodong.
漂亮得不得了啊. My first time was almost 20 years ago. I came here with my grandpa. At that time, I just finished college and get ready to go to States. At that time, I was very young and innocent, and I was so much look forward to all these I know. After being in the States for more than 20 years, I've gone through all sorts of difficulties, and I feel like now I'm climbing Great Wall again. I feel very confident. I know I can get to the top. Come here with my son, and I hope he will follow the step and going to the very top, of his own destination.
For Xiaodong and other Chinese scientists of his generation, it had been a tough climb to the top, surviving poverty and the Cultural Revolution, and securing the rare opportunity to study abroad.
Time is very different now. Back then, China just opened its door, and we really don't know what's lie ahead. And going to the States, we have no idea what I get myself into. But now, with this generation, they have very good understanding what's like living in the States and working in the States, and they may also start looking back at the opportunity, what it's like in China.
Hey,
Back in Dallas, Texas, Xiaodong, other Chinese academics and students often get together for parties and reunions.
Actually, the main thing I'm doing right now, it's probably the most important thing I've ever done and will do in my entire life, is to help China build this institute.
Other people look at Xiaodong more as the glory he has. But I understand him as, the frustration, the sacrifice he had behind his decision to do this. And I'm not sure that would be entirely a successful story as we anticipate. But even though I believe there's something we have to do, that somebody have to try this.
Our generation, we have this idealistic ideas that we believe that China one day will become a major contributor to science and mankind. So that's actually one of the reasons that we go abroad and study, and with the ideas one day we'll bring what we learn back to China.
The 2006 International Conference on Artificial Intelligence, held in Beijing last month.
And this opened up a new era in scientific research in human society. Professor Wu Wenjun.
Chinese mathematician Wu Wenjun is the first to speak, among notables in the field from around the world.
Ideas of Leibniz.
The topic is the future of mathematical mechanization, a field Wu Wenjun revolutionized by making machine proof of geometric theorems possible.
Computer science should have existed long before the advent of computers.
The Mathematical Mechanization Research Center of the Chinese Academy of Sciences. The center was founded by the Chinese government in 1990 to promote and develop Wu Wenjun's work in the field. The 87-year-old mathematician is now the center's honorary director. Digital computers, since their invention in the 1940s, have been used to perform all kinds of computations. but they haven't been too helpful in verifying new or existing geometric theorems, an arbitrary, complicated process that requires human reasoning and imagination. Until Wu Wenjun approached the problem in the 1970s.
The benefit of our method lies in this. We have replaced the genius mental thinking to trivial computations, which may be done by the computer.
To prove a geometric theorem is to show whether a certain conclusion can be deduced from a hypothesis. The essence of Wu's method is to translate abstract geometric relations into algebraic expressions that computers can process.
The hypothesis will be reduced to some polynomial equations, a system of polynomial equations. And the conclusion will become a polynomial equation, a single polynomial equation. This becomes a purely algebraic problem. We have to verify whether a solution of the hypothesis equations will satisfy also the conclusion polynomial equation.
Hundreds of geometric theorems have already been automatically verified using Wu's method.
One may apply this to discover new theorems. You may guess some theorem, then you verify whether my guess is true or not. If it is true, the computer gives the answer that it is true, then you get a new theorem.
This actually helps people to do much higher innovative work because you can leave the computer to do the tedious and sometimes very difficult work.
Many of the researchers at the center are Wu's former students.
Through computers, the mathematical method can be used by many people and in many fields, including robotics, computer vision, even digital camera. We could say that without exaggeration that Professor Wu bring China to the top position in the field alone by himself.
Wu Wenjun was born in Shanghai in 1919. In the same week, what's thought to be China's first ever mass demonstration broke out in Beijing, spawning the May 4th cultural movement. Wu barely finished high school due to the Japanese invasion of China, but with his outstanding grades, he managed to win a scholarship to study mathematics at Jiao Tong University. During Japanese occupation, Wu worked as a high school teacher and had little time for mathematics. The turning point in his career came when a good friend and former classmate offered him a teaching assistant position at a university.
I have enough time to read mathematics again so that I could recover what I had lost during the warfare. I am very fortunate to have such a classmate in helping me so much.
The job was originally offered to that classmate, Zhao Mengyang, but Zhao decided Wu Wenjun needed it more.
让给他什么东西，我就无所谓的。只有他要的，我就给他，因为我佩服他，佩服他的现在。
It was also Zhao Mengyang who arranged for Wu Wenjun to be introduced to world-renowned geometer Chen Xingsheng. In 1946, Wu was hired by Chen Xingsheng to be a researcher at the Mathematics Institute of Academia Sinica. There, Chen said to him, it's time he started making his own contributions to mathematics.
He pointed out that I should not reading and only reading. You should doing research work yourself. Owing to Chen's advice, I turned from mere reading to original research to develop my innovative ability.
At Chen's suggestion, Wu began exploring algebraic topology, and in less than a year mastered some of the most complicated problems in the field. In 1947, Wu left for France for his doctoral studies through a Sino-French exchange program. At the French Center for Scientific Research in Paris, Wu discovered a new set of topological invariants, now known as the Wu classes, which remains one of the most important concepts in topology today. Wu returned to China after 4 years in France. Against his French mentor's advice, and despite an employment offer from Princeton University.
Each intellectual studying abroad, he should come back after he had finished his studying or research works. Yeah. It is a law, general law. No reason.
Wu continued his work in topology in China and won the first-class National Natural Sciences Award in 1956.
数学家吴文俊教授。
Then a seminal wave of political movement swept the newly born People's Republic of China. In the 1958 Great Leap Forward, under Mao Zedong's slogan, more, faster, better, cheaper, impractical sciences such as topology were banned.
Before, I was only interested in mathematics itself, but during the Great Jump period, each mathematician and also scientist was asked to make closer connection with the reality. And I was compelled to do in this way. And I personally, I accept such idea of not leaving reality too much.
He was still trying to come up with a new research direction when the Cultural Revolution erupted. Wu was castigated a bourgeois authority and his home was ransacked twice. He says it hadn't been easy to be a mathematician in China.
There were often political movements. You had to stop your work. And after the political movement is over, it requires a period of time to recover from this movement. You had to change quite often your directions of research in a way not quite willingly so, compared to be so. But I think I learned it in any way.
用这台计算机计算一个200阶的线性代数方程组，只用10几秒钟就能计算出来。
He was later sent to a computer factory for re-education through labor. It was there that he first encountered this new technology.
I was greatly influenced by the great effort of the computers. I began to think computers can do a lot of things what human cannot do. And such a kind of instrument shall be of great help to the research work of mathematics.
Wu, then in his 50s, started learning to write computer programs from the basics. In 1977, in a paper published in the Chinese Science Journal, he showed how it was possible to prove geometric theorems with computers. His discovery was later dubbed Wu's method. Wu Wenjun lives here in the quarters of the Chinese Academy of Sciences. These were among the finest apartments built in Beijing in the early 1980s as part of Deng Xiaoping's effort to rally scientists' support for his four modernizations after 3 decades of political movements. Today, Wu makes occasional trips to the research center and abroad for lectures. Mostly, he works at home in Beijing. His wife Chen Pihe says Wu never had to worry about household chores, cooking, or answering calls.
所有的妻子都支持，都支持自己丈夫。我当然也是这样了。虽然他的业务我不懂，可是呢，要的是时间，要的是亲近。
So that Wu Wenjun can concentrate on these new research topics written on a blackboard in his study.
I have accomplished a little, but I hope I may accomplish much more, and much more.
Tennant's Harbor, Maine. On this land he bought decades ago, mathematician, author, and semi-retired professor David Mumford has his refuge in the woods.
This is my studio. This is where I work all the time that I'm living up here. I have my library from pure math and applied math and neuroscience and artificial intelligence. It's hard to find enough space. What's nice here, I'm sort of surrounded by the artwork of my family. The funny thing is that I'm the mathematician in the family, but almost everyone else seems to be in some form of art.
David did his PhD thesis at Harvard University on pure maths, algebraic geometry.
Algebraic geometry is a fascinating field, and I think what drew me to it was the way in which same geometric objects could be described by algebra and also by pictures of things that you could actually see.
Simply, algebraic geometry is the use of an algebraic equation to describe a line, a curve, or circle, or even a surface. For example, this equation denotes a line. This, a circle or curve. Mumford focused on a 19th century concept called the moduli space of curves.
All kinds of beautiful curves can be produced by more complicated equations with higher powers in them. So then the problem arose in the middle of the 19th century. How many essentially distinct curves are there? What you do is you say, well, let's just take one of each kind of distinct type of curve, and we put them together as points, and this becomes like a map. This whole thing then goes under the big name, the moduli space of curves. And it was tremendously exciting. I worked very hard for a long time trying to take this moduli space, and instead of it being an abstract mathematical thing, I wanted to prove some theorems about the nature of this space. You have the strong feeling as a mathematician, you are somehow reading in this book of absolute mathematical truths that's been there forever, but no one before you has been able to read this book. And so the excitement of it is to try to get a little deeper and find out some facts. And all you have are your bare hands.
David won the coveted maths prize, the Fields Medal, in 1974. Hong Kong-born Dr. Tai Sing Lee is a computer science professor at Carnegie Mellon University. Lee was a graduate student of David Mumford during David's over 3 decades teaching at Harvard.
So he could be called like one of the foundation father of the modern algebraic geometry. So what he has done is equivalent to a paradigm shift. He made the whole field more rigorous. Basically, he is able to bring his educated eye to see simplicity, to get at the essence of things from very complicated phenomena, and bring that kind of educated eye to the field of computer vision and biological visions.
In the 1980s, David Mumford switched from pure maths to applied maths, specifically in computer and biological visions.
I actually built myself a computer when I was in high school with 100 relays. And it worked for about half an hour, and then it had a huge spark came and it burned up. I said, I'd better stick to paper and pencil. In the mid-80s, went back to this. What happened was quite a lot of fun. I went to a meeting in this incredibly beautiful place in Italy. My friend Jayant Shah and we were sipping scotch on the balcony of this hotel room looking over the Mediterranean, and we said, well, I wonder what's happening in artificial intelligence. It's very exciting. You suddenly get seized by a certain excitement that you're going to try something new. And so we did.
Oh, wow. That's a nice one. That's
Wow.
a good one. Yeah.
And the big surprise when I began studying computer vision was that it was hard. It seems almost trivial that you look out at the world, you see the objects in front of you. Why can't a computer do that?
So the first thing David tackled was how computers can be programmed to segment images.
You take a picture of these rocks and you say to yourself, What are the objects present in that scene? You have the seaweed and the rocks and the water behind. Now, if you were to try to segment this, you'll find the computer completely confused. How many rocks should he consider as separate objects? What it should realize is that these rocks is really just one texture, and it really should be grouped into a single part of the image.
David proposed using variational calculus.
And we can set up some functional whose minima is going to give us these segmentations. Except that unfortunately it doesn't work very well. Images are more complicated.
Take the human face. It can be distorted by illumination and varying proportions.
So you have to do some sort of a warping of the face. So we created a probabilistic model of the face.
Incorporating all these ways in which one template of a face could be made to reproduce an arbitrary picture of a face.
This was a really new problem in statistical pattern recognition. Most recently, of course, people would like to recognize terrorists when they pass through customs and immigration control. So there are many companies now doing this sort of thing.
Then David realized imagery was even more complicated. For example, how could a computer detect tanks or false alarms in a forest?
The forest is cluttered. Scenes of the world are cluttered. They have tiny things present and big things present. And sometimes the tiny thing is the important thing, and the big thing is fairly irrelevant. You have to take into account that images have what we call a multi-scale nature. And synthesize in your model this complicated, cluttered structure.
Finding the right probability models to really describe patterns and images is still being tackled by David and his graduate students at Brown University, where he has been professor of applied mathematics since leaving Harvard in the mid-1990s.
Trying to match faces to see whether we can learn computer to distinguish, for example, between different races, Caucasian, Asian, African.
It is actually very useful stuff for fields like medical imaging, for creating pre-diagnostic software to help doctors to see whether a patient is sick or not.
One of the goals, I think, in medicine today is to develop on the computer universal models of the human body, three-dimensional, with all the structures within the body. It connected to my older ideas about the moduli space in pure math, where we were producing this map of all of the objects of a certain kind that could exist.
But for this medical atlas,
this map should have points in it which describe the shape of every single heart that is possible in a human being, or every single brain.
David believes some imaging problems can be resolved imminently.
Medical imaging is one which is really right around the corner. Computers will be able to drive cars without the intervention of human beings. But it's hard to foresee exactly when a computer will be able to attain human skills in looking at an image of the world and being able to name the objects present in it.
Rich in imagery is the Tennants Harbour home of David Mumford. Now 69, he was born in Sussex, England, of an English father and American mother. He came to the US at age 3 and attended Exeter and Harvard. His first wife, Erica, an award-winning poet, died of breast cancer. Second wife, Jennifer, is a professional artist.
You take this heat gun. It will melt the wax so that it moves around a great deal, and then you can draw into it. Yeah. So they were. Well, we're still trying to figure out which spore print to use here.
I mean, you know what I really love about your stuff? It starts with
it starts with something
the actual
very.
pattern,
it
but
starts
then
with actual something.
you bring out these abstract shapes in it. So this is Jen's son Andrew, who lives on Martha's Vineyard, he does these just gems of pictures of the vineyard and everything. My son is more...
He's an adventurer, and he
he's
likes to
he's
travel.
An adventurer, that's very true.
And he likes to put himself on the edge of things.
When he was 20...
Very much like his father.
This one is Baghdad. He spent about a year after the American invasion doing watercolors and drawings. My own sister is an artist. My second son is a photographer.
Greatly artistic family, but you are colorblind.
Yeah, I know. Yeah, many paintings. I can see the yellow-blue, but the red-green is...
And you relate maths with art. Can you tell us something about that?
Yeah, well, form is very exciting to me, and shapes.
So Jennifer, do you see art in maths?
Well, to tell you the truth, I think that the process of creativity is somewhat the same. I mean, you hope that you'll be able to think outside the box and create things. But to tell you the truth, I don't have a clue. I don't have any idea what David does. I mean, he's explained it, but I just, it's a whole different world.
So Hannah, how do you like math?
Some of my favorite subjects.
Really?
Yeah.
Oh gosh, there's so many people who I meet and they say, oh, I hated math, and here I am, a mathematician. It's wonderful to hear that. They should make it seem more interesting and concrete for people in your position.
Like one of David's own pet projects at Brown University.
A really challenging experience was to try to devise a course which would appeal to undergraduates who otherwise are going into history, economics, literature, some of the beauties of mathematics.
David Mumford plans to retire next year. He hopes to visit often his huge and scattered family.
That's definitely going to be one of the great advantages of being retired.
The seasoned sailor also plans to take a long boat trip to the Bahamas.
You feel a certain sense of freedom, which for me there's no other way to get it.